This recording is for Chapter 3, Section 4, Part 2. So we're going to pick up where we left off with yesterday's lesson on 3.4. So if you guys would open back up to where you left off, we will continue. So we're right about page 280. The last thing that we were talking about, we're finding polynomials back from known zeros and also working with complex zeros, and remembering that if a complex number is a zero of a function, its conjugate has to be a zero as well. So that's just a recap on what we last talked about with our previous lesson. So let's pick up with checkpoint number 7 on page 280 and do just another practice. So this one has the function 3x cubed minus 2x squared plus 48x minus 32, and it gives us that 4i is a 0. So we have 1. Now remember that if a complex number is a 0, so knowing that 4i is a 0, negative 4i must be as well. Now if we were to find the factors that led to these zeros, okay, and get those factors out of our function, it would give us what's left over that we could then probably pretty easily determine the remaining zeros from. So what I'm going to do is list the two factors that would have had these two zeros. So 4i would have come from x minus 4i. 4 minus, or negative 4i would have come from an x plus 4i. So if I multiply these two together, I'm going to come up with a product that would make up part of our function. Okay, so going ahead and doing my FOIL, I have x squared. I'm going to have a positive 4xi. I'm going to have a negative 4xi. And I'm going to have a negative 16i squared. Okay, well these two are going to take each other out. And I'm going to be left with x squared plus 16, because remember I squared is a negative 1. All right, so these two zeros come from this factor combination. Okay, so the product of their factors gets us to x squared plus 16. I'm going to divide that out. Okay, if I divide that out of my initial function, it should leave me what else would be multiplied to the x squared plus 16 to give me the entire bit. So take it out. We've done these long divisions. So take a look at your x squared front here. It would take a 3x to get the 3x cubed. Now 3x times 16 is going to be 48x. Don't put it under your x squared term. Put it under your other plain x term. So I'm going to slide it over here and write it down, because then I can combine my like terms when I subtract. So subtracting, the 3x cubes are gone. The 48x's are going to be gone. I'm just going to drop down what I have not yet used. So it would take a negative 2 to make the negative 2x squared. And doing my multiplication, I'm going to get a negative 2x squared. And nicely enough, a minus 32. And everything is gone. So when I take out that x squared plus 16, I'm left with 3x minus 2. Well, that's not going to be hard to figure out what our remaining zero is if that's the polynomial we're left with when we take our two known zeros out. Okay, so if this is our remaining factor, a positive 2/3 is my remaining zero. Okay, so all three of my zeros, they gave us this one, which means we also have this one, and we just determined through long division that 2/3 would be our final zero. Now on checkpoint number 8 on page 281, it asks us to write each function as the product of linear factors and to list all the zeros. All right, so we need to come up with those individual factors and zeros. Okay, so taking a look at this one, Again, there are a number of ways that you could go at this one. This particular function has a fourth power and a second power. So it looks to me like we're going to be able to probably factor this. You could do the trial and error thing with your synthetic division if you wanted. But for me, and for many of you, this is just going to be faster. So my negative 9 is going to break into a 9 and a 1. I'm going to want a positive 9 and a negative 1 to get that 8 in the center. Okay, now looking at these, they both have squareds. X squared plus 9 I cannot easily break, so I'm going to hang on to that one for just a second. So just carry that along for now. But the x squared minus 1 is a difference of perfect squares. So that's a fast one to break. X minus 1, x plus 1. All right, so I can see pretty easily a couple of my factors. It's going to be easy to determine the zeros for those factors. Let's now focus at that x squared plus 9 out front. Now finding the zeros for that, I'm going to go ahead and set that last factor equal to 0 and solve with algebra. If we do some extracting of squares, x is going to equal the plus or minus root of negative 9, which is plus or minus 3i. Okay, so back to our directions. List out all my zeros. All right, well, I have a 1 and a negative 1. That came from these two. And I just found 3i and negative 3i. So here are my zeros. Okay, now the factors that give me those. Okay, well, we saw x minus 1 and x plus 1. 3i would have come from an x minus 3i, and negative 3i would have come from an x plus 3i. Kind of ran out of room there. Okay, there's my product of factors. Okay, so the product of linear factors, here it is. Line them up that you're going to multiply them all together. Product of linear factors. And then right above it, we have listed all of our zeros. All right, let's take a look at this one. Let's do another one. Now on this one, we're not handed a 0. We do not have something that's readily factorable because we have a third degree polynomial, and it does not look like factoring by grouping is going to apply to this one. So I figure out all of my possible zeros. Negative 5 at the end for my constant term. I'd have factors of plus or minus 1 or plus or minus 5. My lead coefficient is a 1, which is nice. I only have options of plus or minus 1 for that. So here are all of my possibilities, and you're just going to have to start testing just like we were doing yesterday. So nicely enough on this one, and generally I do just start with positive 1. Listing out my coefficients here, I did find that 1 was in fact a 0. So I know this is going to be a 0. So go ahead and list it. And the remaining polynomial that I'm going to have is this. Now, in looking at that one, it is an x squared trinomial, but there's no way to break a 5 and come up with a 2. So I'm going to have to apply quadratic formula to this one, I feel, to come up with my zeros. So in doing that, I've got, if you remember quadratic formula, negative b plus or minus square root b squared minus 4ac all over 2a. So negative b is going to be 2. B squared would be 4. 4 times a times c all over 2 times a. Simplifying. I'm going to end up with 4 minus 20 underneath my radical, which is going to be a negative 16. Square root of negative 16 will be 4i. Since both parts of my top can be reduced by 2, I can simplify or reduce the 2's out of here. So I end up with 1 plus or minus 2i. Okay, so I have one real 0, and then I have two complex or imaginary zeros. So 1 plus 2i, and put it underneath here, 1 minus 2i are my other two zeros. Oh, maybe this is still in that same section there. Let's write our product of factors. So the first factor is going to be an x minus 1. My second one is going to be an x minus that 1 plus 2i. And the next one is going to be, whoops, I put the parenthesis in the wrong side here. Let me rewrite that one. X minus the 1 plus 2i. And also x minus the 1 minus 2i. And there's your list of linear, or list of factors. Now, the remaining stuff that we have to talk about, this is going to give us ways in which we can narrow down the trial and errors or narrow down the possibilities that we have for some zeros. So this first thing to consider is something that the textbook calls variations in sign. So in other words, when two consecutive terms have coefficients with different signs, so alternating from positive to negative. All right, so for example, the function that I put on this slide here, x cubed minus 3x plus 2. This one goes from positive to negative right here. There's one variation in sign. Then I go from this one being negative to this one being positive. There's another variation in sign. It went positive to negative, negative to positive. Two variations in sign. Okay, now what is that going to offer us? Well, here we go. There's something called Descartes' rule of signs. This is going to help us try to find out how many real zeros there are. Okay, now real zeros, of course, are going to be things that are not in that imaginary complex system. So looking for these, two things to consider. Okay, for your function given to you, for f of x, the number of positive real zeros is going to be equal to the number of variations in sign, or less than that by an even amount. Okay, so let me translate real quick. Let's pretend, for example, that we found in our function that we had 3 variations in sign. Okay? That means we're either going to have 3 real zeros or 1. Okay, it's going to go down by 2s, going to go down by that even amount. If you had 5 variations in sign, so maybe we have a really big function, and it changed by 5. Okay, it went plus minus plus minus plus minus 5 times. You're either going to have 5 positive reals, 3 positive reals, or 1 positive real. Okay? Now, you're also going to do a check on f of negative x. Now remember, f of negative x is replacing all of the x's in your function by a negative x. And now kind of repeat this whole variation of sign process. If after you've substituted your negative x into your function, you find that the number of negative real zeros will be equal to the number of variations in sign or less than that by an even amount. Okay, so we use f of negative x to figure out how many negative reals there are. We stick with the plain old f of positive x that they hand you to figure out how many positive reals there are. Okay? All right, let's practice this one once. Determine the possible numbers of positive and negative real zeros of the given function. Okay, so in our f of x equation, so our f of positive x, we have one variation of sign. We have two variations of sign. It goes back from negative to positive again. We have 3 variations in sign. So that means we are going to have either 3 positive real zeros or just 1 positive real zero. Okay, we'll have to start checking to figure out which one, but this does tell us that we're going to have some positive real zeros. All right, let's do the f of negative x. So plugging in negative x to our function. Okay, see how all I did for f of negative x was to replace my x's in the original one with negative x's? So if I have a negative 2 times negative x to the third, that's actually 4 negative signs. This front term will be a positive 2x cubed. 5 times negative x squared is a positive 5x squared. Negative negative x is plus x, and plus 8. So notice from beginning to end on this one, there are no variations in sign. None. It's all positive. So there are no negative real zeros. Okay, so don't check any negative numbers. There aren't going to be any negative real zeros. Okay, so this variation of sign, is it absolutely positively necessary to be successful find the zeros of your polynomial? No, not necessarily. But could it be a true time saver? Absolutely. Think of some of those problems that we did that had, 16 some possibilities, plus and minuses of this, that, and the other thing. Well, according to this variation in sign, this one is not going to have any negative reals. Don't check any of the negative options. Focus on the positive. All right, here's another thing that could be a time saver for us, upper and lower bound rules. If you have a factor, okay, so if we have an x minus c factor, and we take it out using synthetic division, okay, we're good at that, we know how to do that. If c, okay, so if that number in the factor was greater than 0, and each number left over in the bottom row of your synthetic division is either positive or a 0, C's the biggest 0 you're going to find. Okay, so whatever that number was, if the entire bottom row of your synthetic division is 0 or higher, it's the highest number that's going to be a 0. Don't check any options that would be bigger than that digit. Okay, well, what if C was less than 0? Okay, maybe that number in there was a negative factor. Then if you find that the numbers in the bottom row alternate, positive, negative, positive, negative, positive, negative, then C is the smallest real 0 that you're going to find. Check the ones that are bigger than it. Don't check any of the ones that would be less than it. Okay, so again, this is kind of one of those things that if you don't remember this, you can still use your trial and error to come up with these zeros. But if you remember upper and lower bound rules or that Descartes rule, it's going to help you save time because you'll know which ones not to bother with. Okay, so let's give this thing a try. Find all the real zeros of this one. All right, so let's try to figure out our options first of all. So my negative 3 at the end gives me options of plus or minus 1 and plus or minus 3. My lead coefficient is an 8. So I have quite a few of them for my lead coefficient this time. And I need to find one factor. I need to find a beginning point. So I did try a bunch of different things. I actually came up with 1/2. Okay, using the 1 on top and the 2 on the bottom. I did find that 1/2. Okay, that took a lot of trial and error, by the way, for me to get to that one. So I had already checked positive and negative 1. I had already checked positive and negative 3. So then I went on into combinations of, those top numbers with my 2. So I came up with 1/2. Now watch what happens when I divide out that one. 1/2 times 0, of course, is 0. 1/2 times 6 is 3. So notice how that one did work. 1/2 is a 0. Take a look at the digits in your bottom row. Okay, they are all 0 or higher. So that means 1/2 is the biggest 0 in this problem. Okay, so it tells me that I wouldn't have had to have checked the 1 and 3. Unfortunately, I already done that. But it's going to be things, and actually things like 3/4. You know, if we use the 3 on the top and the 4 on the bottom, don't bother, because 3/4 is bigger than 1/2. Okay, so I guess there's still a few that it's going to eliminate for us. It would eliminate 3/2. You know, I wouldn't bother with positive 3/2 as an option. Okay, so it's a time saver. If I didn't remember that, I would continue going through the rest of my trial and errors until I figured out whether or not I had any more. Now, personally myself, you know, if I take these bottom numbers here and I write my remaining polynomial, okay, with that 0 in the middle, there's no x term. If I'm going to take this and set it equal to 0 to find my remaining zeros, I'm going to be finding the square root of a negative number. Okay? Think about what's going to happen here. If I move the 6 to the other side, I'm going to have x squared is equal to negative 6/8, and I'm going to have to take the square root of that. I know I'm going to get i's out of that. Okay, there are no real zeros left in this one. Okay, so now I want you to think back to that Descartes rule. Look at my alternating, or my variations in sign here. I went, here's one variation, it went positive, negative, negative, positive, there's another. Positive, negative, there's another. There were 3 variations in my original function. Okay, so I knew there was either going to be 3 positive reals for zeros or 1. Okay, let's take a look at what happens when I do f of negative x. I'd have had 8 times a negative x cubed minus 4 times a negative x squared plus 6 times negative x, whoops, run out of room here, minus my 3. Well, this is negative 8x cubed. This is going to be negative 4x squared, negative 6x minus 3. Notice, no variations of sign in my negative f of negative x. There are no negative zeros. Okay, so technically I guess I hadn't checked negative 1 and negative 3 because Descartes' rule told me there wouldn't be any negative zeros to be found anyway. Okay, so again, like I said, these are rules that are going to save you time if you use them. If you don't use them, you're just going to have more trial and errors than somebody else might. Okay, let's take a look at checkpoint number 11 on page 284. I'm doing this one because volume is something that we do in fact deal with a lot. So there's one example done for you in the textbook. It says you're designing a candle, and the one in the book is done for us, and we're going to redo it with a different relationship for the pieces of our cone. In the original one it said, you're designing candle making kits. I'm on page 284, by the way. Each kit contains 25 cubic inches of candle wax and a mold for making a pyramid-shaped candle. You want the height of the candle to be 2 inches less than the length of each side of the candle's square base. What should the dimensions of your candle mold be? All right, so the one in the book is done out for us. You can see the formula, they give it to us. Volume is equal to 1/3 base area times height. Okay, and they substitute in expressions that represent those dimensions that were described. Okay, we're going to drop down to the checkpoint, and we're going to redo this problem for, we're going to have 147 cubic inches of candle wax, and we want a height of a pyramid-shaped candle to be 2 inches more than the length of each side. Okay, so let's take down a little bit of this information. First of all, we are still doing the volume of a pyramid candle. That requires this formula. Okay, they are giving us a volume of 147 cubic inches. The base length, we don't know anything about. Okay, so assign your variable to your base length. Now the height, they gave us a little bit of a hint. They wanted our height to be 2 more than the length of the base. Here we go. 2 more than the length of that base. All right, so now we're going to figure out what the possible base lengths could be. Okay, now in my formula I need base area. Well, if the base length is x and it's square, capital B, would it make sense then to say that capital B is x squared? It would be x by x. You know, here's your bottom. If it's a square base with length of x, x times x would give us the area. Okay, so capital B is x squared in this one. Let's fill in our other stuff. They hand us the volume. 1/3 is part of the formula. Base area is x times x, or x squared. And my height is the expression x plus 2. Okay, now let's start calculating here. First thing I'm going to do is get rid of that 1/3 over on the right-hand side. So I multiplied both sides by 3. That makes a 441 here. My fraction's gone. I can multiply the right-hand side together. So distribute. And then I brought the 441 over to join the party. Now I still need to find what numbers would possibly work in this. What are the zeros to this polynomial? All right, well, it might take you a while to figure out all the factors of a negative 441, but just start checking stuff. You will find that the possibilities for negative 441, plus or minus 1, of course, 7, 9, 49, 63, and 441. And so we start checking them. Okay, so to make a little bit shorter time of this, the 1 and the negative 1 didn't work. Okay, so I went on to my 7. In checking 7 through my synthetic division, don't forget to put your 0 in here. There was no regular x term in this problem. Don't leave that out. That'll mess you up. So I ended up with x squared plus 9x plus 63 remaining. I then popped that in to see if I could factor it some more. I couldn't find any way to break a 63 and come up with a 9, so I did punch this into quadratic formula. Ended up giving me a negative square root part. There are no more real zeros coming from what's left out of my function. So 7 is my only positive real zero. Now thinking about this one too, I know I put all of the options I had up there for a 441, but lengths of bases of a rectangle couldn't possibly be negative. So really the only ones to test on this one would have been the 1, the 7, the 9, the 49, the 63, and the 441 only. All right, we never would have been able to have a negative 9 base length, for example. All right, so my base length is 7. And it must be inches to match my problem. And then I also should be able to figure out my height now. If my height was, or my base length was 7, my height is x plus 2. So my pyramid must need to be 9 inches tall. Okay. So just an application of how we can possibly use this process. All right, your assignment is to pick up where you left off. I had suggested right around 1 through 50, playing around with those for the first half of the chapter, so that leaves us 51 to 131 for this part. There's a lot, okay, but some of you need to practice more. You're not doing enough of the practice homework problems to get comfortable and familiar with these skills, so please, please, please do more. All right, come to class with questions if you have any.